Okay, so welcome back, and let's talk about the BC normal form decomposition, and we plan to provide the formal description for the algorithm we can use. So in the BC normal form decomposition, we generally need to find a FD which can violate the BC normal form condition, right? Because before we do the decomposition, we first need to check if the relation is in the BC normal form or not. If not, we can always find a FD, right, which violates the BC normal form conditions. And we can describe the violating FD as shown here. A1 to AN implies B1 to BN. So normally we plan to choose this FD, which violates the BC normal form conditions to make this B1 to BN as large as possible. So what does this mean? Given a violating FD, normally we can have A1 to AN implies some B, right? And by computing the closure of A1 to AN, we can make this B1 to BN part very large, which composes the closure of A1 to AN. The main reason to make this B1 to BN as large as possible is to avoid redoing the decomposition many times on the relation. We'll show you why we do this later. And based on the violating FD, we can describe the decomposition rule as like this. We can find a violating FD and we can make the tail part as large as possible. Then the head together with the tail attributes in the violating FD, they will compose a new relation, R1. And we will combine the A attributes with the remaining attributes in the relation, and they will compose another relation R2 as shown here. So R1 will be a new relation including the A attributes and the B attributes. R2 will be another relation covering A attributes with the remaining attributes in the relation. So in this way, we can decompose a relation into two relations, R1 and R2. In the new R1 relation, we have A and B as attributes, right? For R2, we have A and others as attributes. However, for this R1 and R2, we may still have some other violating FDs in them, right? Therefore, we have to continue doing this decomposition until there is no violating FDs in the relations. So decomposition can have several steps. We do this iteratively until we cannot find any violating FDs in the relation. And we can provide you with another example. Let's assume we have a relation of a person, right? We have SSN, name, age, eye color, and phone number as the attributes. At the same time, in this relation, we can find a FD, which is SSN implies name, age, and eye color. According to the previous description, we see that SSN cannot imply phone number, right? Therefore, we can say SSN is not a super key for the relation. According to the definition of BC normal form, we can conclude this relation is not in the BC normal form because we can find one violating FD. SSN implies name, age, and eye color. At the same time, SSN is not a super key, right? So we have to decompose this relation into a smaller relation instead. According to the previous page, we will decompose this relation into two relations, R1 and R2. R1 includes A and B, R2 includes A's and others. According to this rule, we can decompose this relation into two relations. The first one is including the SSN, name, age, and eye color. We define a relation as person, right? This is the A attributes we showed before. This is the B attributes we showed before, right? We combine these A and B's together from a new relation. At the same time, we also combine the A's with the other attributes phone number. They will compose another relation, SSN phone number. We will give it a name, the phone information of a person. In this way, we can decompose the original relation into two relations, right? This is R1, this is R2. We can also find that they are both in the BC normal form. For the first one, we can find a FD. SSN implies name, age, and eye color. And the SSN is also super key for the relation. Then we can say this person, this new relation, is in the BC normal form. At the same time, for the second one, we cannot find any FDs, right? Then we can say this second one is also in the BC normal form because we cannot find any violating FDs in the relation. So this is to do the decomposition for the relation as shown here. Let's assume if we have another attribute in the original relation besides SSN, name, age, icon, and phone number, we have another attribute which is draft worthy. At the same time, we have one more FD, which is age implies draft worthy. Then how can we do the decomposition? So we can provide decomposition later. We plan to show the algorithm first. Based on knowledge we know already, we should be able to know the algorithm already. And let's provide you with a formal description for the BC normal form decomposition algorithm. So formula given the relation inputs as well as a set of FDs of the relation, which is the S set. So in the algorithm, we can compute the FD closure first, which can be denoted as S plus. At the same time, we can also compute the keys for the relation based on the knowledge we know before, right? And based on the S closure together with the keys for the relation, we can check if the relation R is in the BC normal form or not. If not, then we can find one violating FD, right? Then we can find one violating FD, which is F, A implies B. We plan to make this B as large as possible, then we can expand the B by computing the closure of A plus at B, right? In this way, we can make this B as large as possible. And according to the description, based on this violating FD, and we can create two new relations. This R1 is based on the attributes A's as well as B's, right? We can create a new relation R1 with A's and B's as the attributes. At the same time, we can also create another relation R2, right, with A's and other attributes in the relation as a new relation. So based on these two new relations, we can further compute all the FDs over R1 by using this R and S plus, and then compute the keys for the R1, right? And we'll do the same thing for the R2 as well, because we need to first check if there still exists some violating FDs in R1 and R2 or not. And we'll repeat this step 3 for R1 and R2. Again, if we can find any violating FDs in them. If we can no longer find any violating FDs, we will stop and also return these decomposed relations as a result. And we have a special case. We will stop as well. We will stop when all the relations are in the BC normal form, or there exist only two attributes in the relation. The first one is easy to understand, right? Because if we have all the relations they are in the BC normal form, that should be good. For the second one, we do not want to decompose all the relations into one single attribute, right? It will be very bad. If we have a table, it covers only one single attribute, it will be a very bad design of a relation. So therefore, if we have a relation with only two attributes, we will also stop as well. Okay, so this is about the algorithm. And let's come back to the example we provided before. So okay, let me provide the description of the problem again. Let's assume we have a relation R with SSN, name, age, icon, phone number, and trustworthy as the attributes. And we can find two FDs in the relation. The first one is SSN implies name, age, and icon. The second one is age implies trustworthy. We plan to decompose this relation R into BC normal form relation instead. And we'll provide a screenshot of this algorithm in this page as well at the right hand side, so you can see this. And we will do the decomposition according to this algorithm. And you can compute this S closure by yourself as well as the keys for the relation by yourself. And we will manufacture shown step 3 in this page. So given the relation as well as the FDs, we can find a violating FD, right? Which is SSN implies name, age, and icon. We say this one is violating because we find this SSN is not a key for the relation, right? And then we can say this relation is not in the BC normal form. According to the algorithm, we can find one violating FD, A implies B, and we need to further expand this B as large as possible by computing this A closure, right? So based on the relation as well as FDs, we can compute this SSN closure equals to what? I hope you still remember the closure of the attributes, right? You can check back how to compute the closure of the attributes. So given the SSN implies name, age, and I corner, we know that SSN closure equals to what? Equals to SSN first, right? Then age, I corner, right? We check the first FD we have, and then we first check the second FD, right? We have age implies trustworthy. We have age here, then we can say we also need to include the trustworthy into our relation as well. And we have the closure of the SSN equals to SSN name, age, I corner, and trustworthy. Right. So we have so by expanding this B part, we can have a new FD which is equals to what? Which equals to SSN implies SSN name, age, I corner, as well as trustworthy. Right. We expand this B part by including more attributes inside it. Then according to the algorithm, we need to decompose this relation into two parts, right? We have R1 equals to what? R1 includes SSN, name, age, I corner, and trustworthy as attributes, right? This is one relation we can create by decomposing the original relation. We also have R2, right? R2 includes what? SSN as well as phone number. So the first step we can do, right? In the iteration, the first step in the iteration. Besides step 1, we also need to further check, right? We need to first check the R1 and R2 as well to see if we can find some violating FDs or not. So we can have the step 2, right? In the step 2, what we do here is to check R1 and R2, right? So according to our knowledge, we find that R2 should be safe, right? Because in R2 we cannot find any violating FDs. Because R2 has no FD at all, so we can say R2 is in the BC normal form. And here we can further show on R1, right? And for R1, we can find the one violating FD. We have age implies trustworthy inside it, right? It's R1. Here we are focusing on. So we can find a violating FD, right? Which is age implies trustworthy, right? So according to the algorithm, we also need to expand the B side. So by computing the closure of age, it equals to what? It equals to age trustworthy, right? We cannot include more attributes inside it because we cannot find any other FDs which can have the age as a head. Therefore, according to the algorithm, we further need to decompose this R1 into two relations, right? Into like R11, for example. R11 includes what? R11 includes the A and B, right? Therefore, we have age and trustworthy, as well as R12, right? R12 includes this age as the other attributes in the relation, which include SSN, name, age, and I corner. So this is step 2. Should we stop here? According to the algorithm, is no, right? We need to further check R11 as with R12 as well. So therefore, we have step 3, R11 and R12. Right? You can do it by yourself, and we can find this R11 and R12 should be both in the BC normal form, and we will stop, right? Therefore, according to the algorithm, we can decompose this relation we provide in this example into 3 relations, right? So we decompose this R1, so we decompose this relation R into what? The first one we can get is R11, right? It is age and trustworthy. The second one we can get is R12, age, SSN. For the age, here this one is duplicated, therefore we can remove it. We have age here, right? So R12 should be SSN, name, age, and eye color. And the third one we can get is R2. Remember, we have R2 here. So we can decompose this relation R into 3 relations, R11, R12, and R2. And we can also check them, they are all in the BC normal form, right? So this is the example we provide in the slides. By adding this new relation, by adding this new attributes, trustworthy, and the new FD age implies trustworthy, the decomposition result will be very different from the previous ones, right? Okay, so I hope you can follow me in the example and also can understand this algorithm we provide here. And we need to do this iteratively until top criteria can meet, right? All the relations are in the BC normal form, or they contain only 2 attributes. Okay, so that's it for the BC normal form decomposition.